I'm Kinry Watson, and today we're going to be putting trigonometry back together.
Hey, hello! Last time we put together this weird thing called the unit circle so that we could start doing that to things that are curvy and not just things that are straight. But before we go on, let's see if there's more we can do with the unit circle. In this video, we're going to be graphing trigonometric functions based on the ratios that we've learned in earlier videos, because most courses that teach trigonometry expect you to know these functions by the time you finish, and they come from the unit circle. Let's get started. The first function is sine. And so what we're going to do is take a look at the unit circle to get our preliminary table of values. Because when we ask for the sine value of something, what we're really asking is, at a given distance around the unit circle, how high up are we? And so at our first quadrantal point, we're 0% of the way around the unit circle, and our height is 0. And so when x is 0, sine of x is 0. This is also true of 2 pi when we go all the way around the unit circle, and negative 2 pi when we go all the way around the other way. Our next quadrantal point is pi over 2, and that means we're a quarter way around the unit circle, and our height is 1. So pi over 2 is 1 when x is pi over 2. This is also true for negative pi over 2, which is when you go the other way. Our next quadrantal point is pi, which is halfway around the unit circle, and our height is 0 again. And our final quadrantal point is 3 pi over 2, so 3/4 of the way around the unit circle, and our height is negative 1, so we know that the sine of 3 pi over 2 is negative 1. That's also true for the negative section of the graph. So now that we have these values, we can look at what the sine function looks like actually graphing all the points. You can see 0, 0 at the origin, and you can see the high points at pi over 2, and at pi it touches the axis again at 0, which is what we got from our table of points. And you can see that it's the same going backwards as well. So if this is a graph of sine of x, its period is 2 pi, which on this graph you can see is a little past 6 because 2 pi is approximately 6.28. The amplitude of sine of x by itself is just 1 because the radius of the unit circle is 1. So now we're going to take a look at a transformation of the sine function. So we can see this is sine of x plus 2 in purple because the period is the same and the amplitude is the same. The only thing that's changed between those two functions was the location of the central axis. And so that's why we write plus 2 to indicate that it's up 2. Next, let's look at a transformation of the amplitude. So in black, we have sine of x with a normal amplitude reaching to 1. And in blue, we have a sine function with an amplitude reaching to 2. So we can see that the amplitude is 2 in the blue, and so the way that we would write it is 2 sine of x instead of sine of x. Here we have a transformation of the period, which is to say how long the graph goes before repeating again. In a regular sine function, the period is 2 pi, which means after you've gone a full way around the unit circle, the graph starts again, which makes sense. So when the period of the graph that we see in green is shorter, what that means is that it repeats sooner. It repeats when sine of x reaches its halfway point, and so its period is 2x. Now let's try to put them all together. So we're going to try to graph this function, 3 sine of 3x minus 1 plus 3. So here's our original sine function. And so we're going to start by graphing the vertical transformation. So there's the vertical shift up. Let's try applying our next transformation. we'll do the horizontal shift. So we can see from the original sine function in black, we've shifted up and to the right. Our next transformation is going to be the transformation of the period. So you can see that in red, and how it goes 3 times faster than our original sine function, which is still at the bottom. Finally, we're going to apply the change to the amplitude. And that's what it looks like with our previous transformations applied and the original sine function. So there's our original sine function. There's all the transformations put together step by step. And there's our final function, f of x equals 3 sine of 3x minus 1 plus 3. Now let's move on to cosine. We're going back to the unit circle to try to graph another trigonometric ratio, cosine. So where sine was asking, when I'm this far around the unit circle, how high up am I? Cosine is asking, when I'm this far around the unit circle, what's my position on the x-axis? And so at our first quadrantal point, we are 1 over, and that's why the cosine of 0 is 1. Our next quadrantal point, which is a quarter of the way around the unit circle, we have not gone any distance on the x-axis, and so we're at 0 at pi over 2 and at negative pi over 2. The next quadrantal point is pi, and we're halfway around the unit circle and also negative 1 units away from the origin, because the radius of the unit circle is 1. So that's true for pi and for negative pi. And our final quadrantal point is 3 pi over 2, which is 3/4 of the way around the unit circle. And once again, in terms of the x-axis, we have not departed from the origin. So the cosine of 3 pi over 2 is 0, just as the cosine of negative 3 pi over 2 is 0. And when we get back to 2 pi and negative 2 pi, we see that it's the same as 0. It's 1. We'll take a look at our cosine graph. So this is what it looks like when it's not transformed, and we can see our 0 point. It's up at 1, touches the axis, it goes down, touches the axis again, and goes back up. And so just like sine, the period of cosine is 2 pi, because that's when it repeats. But instead of starting at the origin and going up and down and back to the x-axis, cosine starts at the top of its amplitude, goes down and comes back up, and that's what we consider a full period. We're going to try to figure out what the equation is. So that is the axis of the equation of the function, and we can see that it's not the same as the x-axis. So we know that there's a vertical shift, and since it's below the x-axis, 2 down, we know that the vertical shift is negative 2. When we look at the period, we can see that the distance from the first peak of cosine to the second peak is a little bit past 6, and we know that 2 pi, which is cosine of x's untransformed period, is roughly 6.28, so it's reasonable to assume that the period is unchanged. It's still 2 pi. Next, we're going to look at the amplitude of our mystery function. It's definitely bigger than 1, and by counting it, we can see that it is 5. And when we look to see if there's a horizontal shift, there isn't any. So now we have all the important information from the graph to compose our equation. And we can see that this is a graph of the equation y equals 5 cosine of x minus 2. You see it has no change on the period because the period is the same. The period of this function is the same as the period of cosine of x. You can see the change in the amplitude and the vertical shift expressed in the equation. Let's move on to tangent. So we remember that when we were putting points on the unit circle, we saw that sine is the same as the opposite side of our reference triangle over the hypotenuse, and since the hypotenuse is always 1 on the unit circle, it can sort of be disregarded, and so we talk about sine as that opposite side of the triangle. And it's the same with cosine, with the adjacent side of the triangle, because the hypotenuse is 1. But tangent isn't like that, because it's the ratio of the opposite side to the adjacent side. which makes it a little bit more difficult. So let's take a look at our unit circle. Our first quadrantal point, we are 0% of the way around the unit circle. And so our values are 0, right? Our x, because tangent is equal to y over x. And so our y is 0 over 1, and that's 0. And that's also the case for pi and for 2 pi, because negative 1 over 0 is the same as, or negative 0 over 1 is the same as 0 over 1. Our next quadrantal point is actually an asymptote, and that's because when theta is 0, tangent of theta is equal to y over x, right? That's the ratio. And when theta is 0, tangent of theta is equal to 1 over 0, which doesn't exist. And that's the case for both pi over 2 and 3 pi over 2, which sort of makes a problem, right? Because we have our quadrantal points, but all we have is zeros and asymptotes, and that doesn't really tell us much about the behavior of the function. So we're going to try to graph some intermediary points. If we take pi over 4, that's pretty easy because it's root 2 over 2, root 2 over 2, so the y over x are the same, which means that at pi over 4 and at 7 pi over 4, this is going to be 1. So when you look at a tangent graph, you could see that it has all the attributes that we found earlier in our table. You can see they have the asymptotes at pi over 2 and at 3 pi over 2, and also the negative side, which we see in this graph. You can see all the points it intersects at the x-axis, and all the points where it reaches 1 and negative 1. Now, tangent isn't continuous like sine and cosine, but it does still have a period. It continues to repeat as many times as you go around the unit circle to graph it. Now, because we are making all these new functions, let's see if we can make anti-functions for the ones we already had. If you remember talking about arcsine, arccosine, and arctangent in an earlier video with Lucas, you'll know that we have a function called sine of x, where if you put in a value x for how far you went around the unit circle, you get a value y for how high up on the graph you are. And you'll remember that we also made a function where you put in a value x for how high up on the graph you are, and you got a value y for how far around the circle you've gone. And so that's what we mean when we say inverse functions. Our first one is arcsine, which is the inverse of sine. So this is our table of values for sine, which we did earlier. And so to make the inverse of sine, to make arcsine, we know that we take a value, an input value a, and we get a value b for the sine function. For arcsine to be its inverse, you have to input the value b and get the value a. So our arcsine table of values should just be like this, right? We flip the input and output, and it's the same, right? Except if you were to graph all the values, it would look something like this, with the x and y values, the x and y axes for sine to be switched in arcsine. But this is sort of complicated because when you are trying to define arcsine as a function to graph, you have to remember that functions have to pass the vertical line test, and graphing sine to the same extent that graphing arcsine to the same extent that you would graph sine doesn't create a function that passes the vertical line test. So usually arcsine is graphed just in this half period before it overlaps with itself. Next is arccosine, which is the inverse of cosine. So here's our table of values for cosine. And remember, cosine is trying to take an input, x, giving an output, y. And so arccosine has to take the output and give the input. So on the graph, another way to think about it is to think about it as a reflection across the line y equals x. And you can see that here on this graph with cosine in red and arccosine in blue. Just like arcsine, arccosine can't really be graphed to its full period because it wouldn't pass the vertical line test like that. So we just graphed this segment of it. And you can see that it is the inverse of cosine. Arctangent. Arctan is what we're going to do next. And I find it easiest to just start with the graph of this. So you can see the line y equals x between arctangent and tangent, and here's them together. So arctangent is in blue and tangent is in red, and you can see that arctangent, just like arc sine and arc cosine, isn't periodic, isn't repetitive like sine, cosine, and tangent. But what I think is interesting about this is that you can see that the vertical asymptotes in the function tangent of x sort of become horizontal asymptotes for arctangent of x. Yeah, so what we've done in this, and that's pretty much it. What we've done in this video is graphed sine, cosine, and tangent, and arcsine, arc cosine, and arctangent. And we learned where sine, cosine, and tangent are periodic, arcsine, arc cosine, and arctangent are not. Because to define them as functions, they have to pass the vertical line test. We also learned about transforming some of these functions, and we'll be able to spot transformations when we see them in the future. Next time, we'll take a more in-depth look at the functions we graphed today, and we'll talk a little bit more about how they're related to each other. See you then!